Lui, donc, donc Philippe a fait sa thèse qu'il a soutenue en 2016 avec David Quéré et Christophe Clanet sur les problèmes notamment de Leidenfrost. Ensuite, il est parti 2 ans en postdoc au MIT avec Garrett McKinley, où il a plutôt travaillé sur des fluides non newtoniens, si je ne dis pas de bêtises. Et donc 3 ans au MIT et 2 ans ensuite à Princeton avec Stone sur différentes activités, dont certaines dont il va nous parler aujourd'hui. Et Philippe est aussi candidat, donc section 10 pour le labo ici. Et donc on espère que ça marchera. Voilà, et ben je t'en prie.
Merci Thomas, merci à tous d'être là. Donc aujourd'hui je vais parler de... je fais le séminaire en français ou en anglais en fait? Français? Pour tout le monde, c'est bon? Ou... comme vous voulez.
Vous voyez qui est connecté?
Donc je peux faire les deux. Si c'est en français, je vous excuse. Excusez-moi par avance pour une tonne d'anglicisme probable, mais sans ça tout me va. As you want. Like, so. Let's do it in English. Okay, perfect. So I'm going to. So thanks for the introductions, and I'm going to talk today about droplets in the air, and particularly on 2 distinct situations where droplets are surrounded by air and are conveyed by airflows. And so I'll both discuss droplets and airflow and aerodynamics in general. And so one example of droplets in the air has been described recently in the PhD of Pierre-Brice Benten, where he's flowing some airflow from the top of that picture here on the side of a fiber on which he put some droplets on it. And what he observed is the fact that the droplets change the airflow behind it downstreams, and that there is a repulsion between adjacent droplets on that fibers, which leads to that instability where you have motions but non-coalescence of droplets. So when you have an airflow, you can see many weird pattern, let's say, when you have a droplet there. But in that particular example, droplets are attached to a solid, and in the 2 situations I will discuss, we are in the situation when there is no adhesion to a solid of a droplet, and so the droplet is fully surrounded by air. And the first example that I could mention of droplets surrounded by air are this kind of situation here, described by Leidenfrost in the middle of the 18th centuries, where a droplet deposited on a very hot solid, here it's 300 degrees, is fully surrounded by a layer of air. As you can see here, between the droplets and its reflection on the solid, you have a very thin ray of light, which indicates the fact that there is an insulation gap made of vapor. So the droplet is deposited on the earth solid. It creates a thin layer of vapor, and so the droplets sit on that insulation layer. So that's the first situation I will discuss later in a different systems with that temperature. And the second situation that I will discuss is also the fact that droplets by themselves are conveyed by air. So we know that if we are looking on a windy day, kind of droplets in like rain droplets, which can be deviated by wind, but we can also find that in the context of a violent expiratory event like a coughing here, as described by this picture from a book by Wells, by the fact that when we talk, we speak, we cough, we are able to, we generate droplets, and we are very well aware of that now in the context of the pandemic. And those droplets are small enough to be conveyed by the airflow most of the time. And so I will discuss that in 2 different situations, but mostly for singing, basically. And so that will be the outline of my talk for droplets in the air. I will first talk about levitation of droplets and levitation of particular droplets, which are fizzy drops, which has been also fizzy fluids have been also one activity in the lab from Thomas in particular, and then I will discuss about airflow in opera, so all those droplets we emit and all those expiratory airflow direct those droplets in the context of music, and why is it so important for music. So the first part of my talk is something that I've done at MIT with Gareth McKinley, and in collaboration with Divya Pachanathan, who was a PhD student co-advised by Kripa Varanasi and Gareth McKinley, and also with the contribution of Philippe Nicolier, who was a visiting student from Zurich at that time. And so levitation of fizzy drops is something which is new, but levitation of droplets, there are many people who've tried to get that particular state of wetting or of non-wetting actually, which prevents any contact between a liquid and a solid. And so if you prevent any contact, you are able to have remarkable properties where you avoid corrosion, typically you avoid adhesion of liquid on a solid, and that's kind of things are exciting many persons. And there is many ways to do that using magnetic field, but one very elegant way was also discussed by Suzy during a PhD, but by the fact that you can also vibrate a liquid bath of oil, and if you deposit a liquid droplet on top of that bath, on the top of that vibrating bath, if it's the same oil, and you can prevent contact for a very, very long time, and so you have situations where your liquid doesn't touch its substrate, which is liquid in that case. So that's one way to use a force, an external force to the droplet, or an external field to the droplet to prevent coalescence between a liquid and its substrate. In the case of the Leidenfrost effect, that's slightly different in the sense that the levitation is provided also by the liquid inside the droplet. So here you have a solid hot substrate at 300 degrees C. You heat it and you create your vapor. And as you heat your solid, you burn the fuel of your levitation, which is the liquid inside the water inside the droplet, which create vapor. And due to that insulations, you have a lot of very important vapor flows below the drops, and those vapor flow are able to interact with the droplets. And one example of that is has been discussed by Linke when he deposited a water drop on the top of a ratchet substrate. So you have this kind of geometry there with all those teeth and asymmetric teeth on the top of your substrate. The texture are millimetric. You heat your substrate, you have levitation of your droplets, but more importantly, the drop is also directed in a particular direction. So here everything is flat. Everything is horizontal somehow for the substrate. You have no slopes, but when you deposit the droplet is in levitations and is directed in the direction of the large teeth of the substrate. And the reason for that is the following: is the fact that as the droplet is exerting a pressure due to its own weight on the vapor layer behind it, the vapor is forced to flow, and the easiest way to flow for the vapor is basically the largest size of the teeth there. And so, which means that the vapor flow is redirected downward the slope of every single teeth before escaping from the side. And that's the kind of sketch you have here. And as vapor is redirected by the millimetric texture, it entrains by viscosity the droplet. So that's one of the remarkable properties of Leidenfrost drops, in the sense that they are mobile and you can redirect them. And so that's something which has interest for driving droplets in a particular direction in microfluidic typically. But one problem of that effect is the fact that you have to heat your solid, which means you have to get a very high energetic cost to be able to use all those nice properties of provided by the insulation of the droplets. And so the Leidenfrost temperature is known to be on a smooth solid of around 200 degrees. So you have to go far above the boiling point to be able to observe this phenomenon. And so one important question has been to reduce the Leidenfrost temperature to make it more efficient for all those kind of applications. And the first attempt of it and most noticeable attempt of it was done by Wakarelski and collaborators in 2012, where they used a superhydrophobic solid to reduce the critical Leidenfrost temperature down to the boiling point. So they increase the range of levitations for liquid droplets down to the boiling point, thanks to that kind of texture. You see there a CM picture, which is a rough hydrophobic solid, which is superhydrophobic. So that's something I've studied quite extensively during my PhD, and I won't discuss too much about it. But then the next question is, can we do better than that? So we are still at the boiling point. Can we do the same kind of levitation for droplets at ambient temperature? And so if we are at ambient temperature, there is no more evaporation, so we have to find something else to do it. But the key point here is the fact that the solid is superhydrophobic, so I will briefly discuss what superhydrophobicity looks like. So you have this kind of solid here at the submicrometric scale. You have a roughness. This roughness is hydrophobic, and because it's hydrophobic, the liquid doesn't wet. The water doesn't want to wet the solid, so it remains on the top of the texture and doesn't wet a large surface, a large area of the solid. And because of that, the droplet doesn't spread on the solid and adopt this quasi-spherical shape once deposited on a superhydrophobic solid. So that's what it looks when you are looking with a magnified view. You still have contact, but you have a tiny part of your solid which is wetted, as you'll see later. And so that effect has been predicted by Cassie and Baxter on a rough hydrophobic solid, and you can see that on those pictures. You can also see that when you are looking from the bottom of the droplet. So you are using an inverted microscope. You are looking with a monochromatic light here. And with that monochromatic light, you image the base of the drop. And so you see the edge of the drop here, the edge of the base of the drop, and you see all the contact area. And what you see is the fact that you have a myriad of bright and dark spots behind the drop, which indicates the heterogeneous nature of the wetting. So once again, we have a submicrometric texture here, so we are not able to distinguish every single contact point on the base of the drop. But we see that the fact that it's not uniform indicates that you only wet on the top of the texture here. So that's one of the signature of superhydrophobic solid, and that picture has been made with still water, with DI water. What happens now if we go with the commercial sparkling water is the following. So the movie that I'm gonna play has been accelerated 2 times, I think, and I'm gonna play 10 times, and I'm gonna play it. So what you've seen is basically the deposition of the drop, and many things happen after that, and I'll go through it more carefully. So at the very end of the movie, you see the same kind of pattern that before, different size, but very similar. So at the end of the movie, you are back to a Cassie-Baxter state, to that superhydrophobic state, where you have contact. Definitely you have contact between the solid and the liquid. But that contact, once again, is heterogeneous. But before that, the first thing you noticed after deposition of the drop is kind of interferences rings, which indicate that you are purely in levitations above your solid. So you have a very thin gap, a micrometric gap between the bottom interface of your drop and the solid, and the superhydrophobic solid. And you see all those fringes, which indicate you that you have a dimple in the center. More or less. So that's why you start to have fringes which indicates a different height, basically. And so you can get the profile, and you see that there is a bubble in the center, and so it's a dimple surface. But more importantly, the point is that you reach levitation at some point. Once again, the movie is pretty fast because it's accelerated 10 times, but that levitations after 20 or 30 seconds, you start to see some kind of pattern on the side, which indicates that you start to have contact with your solid, and that contact starts from the edge of the drop, the edge of the base of the drop, sorry. And afterwards, what you see that all those contact points are increasing on the edge before moving inwards in the center of the drop. And so at the end of the movie, the entire base is back to a non-levitating system, but you are on a superhydrophobic solid, so you are back to a Cassie-Baxter regime. Okay, that's for the first movie, but I go through it more in details a bit later. Yeah. So here, right now, so the wavelength is basically 500 nanometers, and so what you see between two successive fringes is lambda over 4 between the bright and the dark fringes, so which means you have a difference of height of around 150 nanometers. But so you can reconstruct the interface at the beginning, and so it's not that obvious on the first view, but if you start to identify what is the pattern there, you can see that basically the minimum height, and I'll discuss about it later, will be on the side there. There will be an increase on that side on the edge of the drop, just because you get back to the spherical shape on the external side, and inside you see that there is a dimple basically. But then at the very end, on that effect, you still see fringes somehow, and that's a difference between bright and dark spots. And there is, and so you can reconstruct also the interface, but now the pattern is much more complex, just due to the fact you have contact point locally, and that your solid is not totally flat. It's rough, of course, at a submicronic scale, and that's what you see here. That is, yeah. Okay. So I'll go with a bit more details on that a bit later, but yeah, feel free to let me know if there is any other things unclear. So that was with the commercial sparkling water. So of course we made our own carbonated water by pressurizing a bottle of DI water with CO2. And so if you impose a certain pressure, then you can also measure the concentration of CO2 dissolved in the gas, in the liquid, sorry, by measuring the pH. And you have a correct agreement, which is the ambient law, between the imposed pressure and the concentration of CO2 you measured. But so you get a way to tune the concentration of CO2 within your carbonated water. And what you observe is the following. If you're looking carefully to a drop, you can see that once again there is a ray of light between the drop and its reflection on a superhydrophobic solid. But that ray of light is much thinner than in Leidenfrost, than on the first picture I displayed, adapted to Leidenfrost, to the hot solid. So with a magnified view, you still see the absence of contact between liquid and solid, of course. And once again, it's within few micrometers, that gap. And so the mechanism is the following. You have a supersaturated liquid which wants to release CO2, and that CO2 is released everywhere around the droplet, but it's also the droplet trap some CO2 behind it, and that CO2 spread on the superhydrophobic solid and helps preventing the contact between liquid and solid. But that kind of things, you need still the superhydrophobic solid, because otherwise, I mean, we have never observed levitation on a plastic bottles, which is a container, the usual container of carbonated water, typically. So it requires a superhydrophobic solid. For the same reason, Vakarelski and collaborators have also used the superhydrophobic solid to decrease the Leidenfrost temperature. And the reason for that is the fact that the superhydrophobic solid is also a super aerophilic solid, which means that you basically on that solid you spread easily gas, and so you keep a layer of a very thin layer of gas can be stable thanks to that superhydrophobicity. Okay, there is no instability there; it doesn't destabilize on that particular solid. So the first thing we can do with it is like how to define a levitation time. And so when we are looking at the fringes, it's pretty clear at some point you start to see contact on the edge. And so you can count the time at which that first contact happened. And if you do so, you measure levitation time, tau, as a function of the initial concentration in CO2 within your droplet. And so that's for the same volume of droplets, 40 microliters. You measure the initial concentration, and at the end, thanks to interferences, you measure the levitation time. And what you see is that there is an increase of the levitation time with the concentration. That increase is due to diffusion, actually, is limited by diffusions of CO2 around the droplet. That's the dashed line here, which is our model. I won't enter into the details, but you have all the details in the paper. But also you have, very remarkably, an onset for levitations, a critical concentration of CO2 to provide levitations. And that concentrations happens to be happens to be what it is, but it's an equivalent of the Leidenfrost temperature. So you also need enough CO2 to be able to generate enough flux of CO2 to be able to generate levitation. But the most important things for levitation is, of course, the thickness of the gas layer. And to do so, we use the same system, the same interferomicroscopy setup, but with a magnified view on the edge of the droplet base. So you see the droplet base is with a dimple inside, and if we are looking at the edge, we see these pattern here of fringes. Here it's inside the droplet, and here it's outside the droplet. And when you are taking a movie of that area, you see that over time it starts to be pretty stable initially, which helps you define an initial thickness. But at some point, you have a lot of fringes which go through it, and you can count the number of fringes until you reach a permanent state, which is a contact. And so from the contact, you can count backwards all the number of fringes, and you can estimate the initial thickness of levitation. And so you can measure that initial thickness H0 as a function of the initial concentration of CO2. You still see, of course, these onset CL for levitation. But after that, you have an increased thickness as a function of the initial concentration. But the main point here is that the thickness we measure is always below 3 microns, which is order of magnitude lower than the typical 10 to 100 microns you observed with Leidenfrost drops. Yeah. Yes. So indeed, it will depend on the size of the drop. So the dependency on the size of the drop as a function of for the thickness has been shown in Leidenfrost regime pretty clearly by Anne Lorbiance in 2003. But for those kind of droplets, it's actually pretty challenging to dispense a given volume of liquid because you have to calibrate it properly, like in the sense that when you are pipetting some volume of liquid, you create also bubble and things like that. So we've done that, we've changed a bit the concentration, but we haven't studied the thickness as a function of size. But you expect indeed a change. So you can calibrate that, and then you find that actually it doesn't depend of that. Like it's pretty stable, the concentration that you dispense. But it's just a bit tricky to be sure to repeat the volume as a function of So in that case, you will see afterward that there is a clear dependency you expect from the size of the drop. so because if you want to explain the kind of disagreement between the order of magnitude between Leidenfrost drops and those fizzy drops in terms of levitations, in terms of thickness, you can get back to the equations which model those levitations, which are based on lubrication theory. And in terms of scaling, it's basically saying the fact that the drop, that there is a flow of gas below the drop in that thin gap, insulating the drop from its solid. And that flow is directed by a gradient of pressure between the pressure applied in the center of the drop due to the weight of the drop or capillary pressure, depending on the size of the drop. But that delta P, that gradient of pressure, is exerted on the radius of contact from the center of the drop to the external part of the base. And you can balance this gradient of pressure by the viscous stress, which is basically the viscosity of the gas times the velocity you might expect for the flow of vapor or CO2 in that case in that gap over the thickness, the square of the thickness of the gap. So that simple models only take into account an homogeneous thickness, which is not exactly the case, but which has been, which is an approximation which has been valid for Leidenfrost to predict the thickness. So the other thing you can do is basically you can know what is the mass balance between the amount of CO2 emitted by the droplets to feed the thin gap of CO2 below the drop. And that's scaled with linearly with the velocity of the flow. And so you see that in that scaling, RC is appearing there, which is basically where you find a huge dependency on the volume of the drop. And so all those scaling, if you combine those two scaling, you basically find that the thickness will vary with a flow rate, with the amount of CO2 you generate by unit of time, basically with the flux of CO2 you generate from your drop, with a power 1/3. So the thickness will be reduced by the fact that the flow rate is smaller, like the amount of CO2 you generate is smaller. And the difference between Leidenfrost and those fizzy drops is the fact that you have much less fuel to provide levitation. In the case of a Leidenfrost drop, you consume all the water inside the drop, and so you have the entire volume of liquid you can create vapor with, whereas here you have only a tiny part of your droplet, which doesn't change size, or you cannot measure the difference in size before and after levitations. And you have only a tiny part, which is the amount of CO2 dissolved into the droplet. And so if you do that measurement, you basically get 3 order of magnitude difference in m dot, which explain the order of magnitude you get in the thickness. Okay. But so now you can play with those little hovering objects and try to describe their properties. So the first experiment we've done was to try to quantify the friction of a droplet with a superhydrophobic solid, depending on the concentration of CO2. And so for that experiment, we have a groove or half pipe here, where we are able to release the droplets from the top of the half pipe. There is a constant radius of curvature, very tiny slope because the radius of curvature is pretty large, comparatively to the size of the drop. And then you observe that the drop will move downward on that slope. And for all those movies here, you see from the top here. So on both sides, you have the top of the groove, and in the center, you have the minimum height. You have different concentration from pure DI water without levitation to a higher concentration of CO2 there. And when you track the angle theta as a function of time, you are able to see that those droplets are oscillating, but they stop their oscillations at a time which is shorter for low concentrations, whereas levitations remains effective longer, like at large concentration of CO2. The other thing you can notice is also the fact that, except for the first case where you have no levitation, you have a kind of frequency which is conserved on all the experiment, at least at short time scale. And so that's that frequency. You can compare that with a very simple model where you say that what is at stake there in that experiment is an inertia versus the weight of the drop, which is the motor of that oscillations. And you have one dissipation you can assume for the levitating regime, which is the fact that you have the viscosity of the gas over the speed. And by the scaling, a very simple scaling, you can assume that it's proportional to it's inversely proportional to the thickness. And when you use that experiment, that equation, you see that you have a linearity. You have a damped harmonic oscillator, basically, because your force of friction is linear. Thanks to the levitations, and so you can solve it analytically and find what is the parameter h, which is the thickness, and so you see a very good agreement as a function of concentrations with the thickness measured by microscopy and the thickness that you derive from those measurements here. You see the fit here in red with the experimental data blue, and you see that after a certain time. The harmonicity of the oscillations is lost at the very end, and that is due to the fact that either you have contact after that amount of time, and you start to have contact, and so the friction law is not at all linear in that case, and also by the fact that h is varying over time. So it's pretty stable initially on the first seconds, but after sometimes h starts to decrease until it touches the solid. So that's why you finally lose at a time scale larger than 10 seconds the harmonicity. So, yeah. So that just demonstrates how you reduce even the friction that you have, the very low friction you have on a superhydrophobic solid, by doing that with a carbonated water. You can go back to the original experiment I described from Linke on those ratchets. Now you have a superhydrophobic ratchet. We launch the drop in the opposite direction of the expected motion, and we see what happens. So initially we launch it on the opposite directions. Everything is purely horizontal. There is no slope there. And you see that after some time, the trajectory of the drop reverts and go in the Linke direction, like is redirected by the asymmetry of the solid. But here it's pretty clear that it's much smaller than the first movie I played, and the fact it's much smaller is just because you have also reduced the gas flux from the levitation. So the force of entrainment is much smaller. So now everything. So now you are able to get the same properties as Leidenfrost, but at ambient temperature. Yeah. Yeah. So I think there is always both mode of oscillations, which are due initially to the fact that you launch the drop, and when you detach, it's difficult to control. But indeed, there is a kind of stick slip where you can't feel the texture, and that's because it's getting so slow that the friction on those solids is known to be the friction by the fact that you hit a kind of wall there, and you have a collisions of your. So your liquid is going deep into the texture, and so even if it's insulated by a gas layer, it has to deform to go through a teeth, and so that's probably the reason why at the end the frequency is adapted to the pattern too. So now you have all those properties. You can also start to play with other kind of liquids still at ambient temperature. But basically, the principle is just you have to get an active liquid able to generate gas. And so you can do that differently by displaying on a superhydrophobic solid still, that's a requirement. One acid drop, and you add on it a base, and you see very violent reactions which generate gas. Here CO2 too. So when you mix those two liquids, you will get a lot of CO2. And so that's what happened in that movie, where initially you have only one drop of acid, and when you had the base on it, you release a lot of CO2, and immediately you reach levitations. You still see those fringes there, which are similar to the one I displayed for homemade, for lab-made carbonated water, and you maintain levitation. But it's not just CO2, you can do that with other kind of reactants. In that case, you have a catalyst of the hydrogen peroxide destabilizations, which give you the oxygen, basically. But you see there that the concentration is probably not optimized of reactants, but it takes a while for the droplet to detach from its superhydrophobic solid and to finally get fringes which indicate levitation too. But basically, you can do that also by chemical reactions, able to generate gas. Okay, so I've been a bit slow now. I don't know how long I have before. 10 more minutes? Okay, so I can jump on the other topic, which is pretty different. So maybe we can also, if you have other questions, we can maybe get back to the levitation later or whatever. So the other topic is airflow in opera. So now the droplets are not so large; they are too small to be seen. They are emitted by a speaker or a singer in that case. And we are looking at the airflow, which are basically exhaled by a person. And so that's something we have done in opera because the Met Orchestra contacted us because they were worried due to the pandemic about the possible contaminations when they were rehearsing or they were playing music. So that's a work I've done in Princeton with Howard Stone and Paul with a PhD student there, and in collaboration with Manu Kapkarian, you've recently seen in the lab within Montpellier. So the fact that contamination are airborne, I'm sure you are very well aware of it, is not that new actually. Like if you read that great text by Pasteur about spontaneous generation and the rebuttal of spontaneous generation, he already mentioned kind of dust suspending in air, which are responsible for contaminations, and in the case of fermentation there. But it's also, of course, discussed for disease since a while now. And why music? Because music has been particularly disrupted, like many other things, during the pandemic, and that's the case of the Metropolitan Opera in New York City. And the reason for that is the fact that the first big cluster who helped understanding the aerosol contaminations due to COVID are basically connected with core and rehearsal of singers there. And there is a very dramatic example in Utah there which leads to that basically understanding, and where the analysis of that cluster has shown basically airborne contaminations as a main factor for COVID. So it's not at all new actually in the fact that we generate droplets and that those droplets are contaminating others. That's not at all new, and things have been also demonstrated and discussed since one of the seminal work from Wells in the 30s, where he displayed the fact that we basically emit droplets when we breathe, speak, sing, and that the trajectory of those droplets depend on their size. It's also very well known for music. It has been studied for tuberculosis in '68 previously. And why is it so important for when playing music is basically that when you play music, you increase the amount of droplets that you generate. And so that's two examples associated with music, but there are many others of measurements of number of droplets. And so you see that particularly there is few activity which are identified as very, very risky, let's say, in terms of contaminations. Loud singing And in terms of instruments, wind instruments, but particularly trombone, oboe, and trumpet. And we'll try to identify in the context of an orchestra if the number of droplets, so the number of droplets is well known, but we'll try to find if airflows are also enhancing that risk, or what kind of airflow are basically the most at risk for different instruments. So what we did was getting the chance to get great musicians and singers in the lab, and we were able to perform experiments with them and to visualize the airflow. And one thing we've done was using an infrared camera, which is able to capture, of course, the temperature of the warm face of the singer. Here is Angel Blue, a soprano, but also to capture with a filter basically the warm CO2 exhaled by the person. And so Angel is singing. I'll let you enjoy that. So she's singing the very end of a very famous part of a Norma, of an opera by Bellini, Norma, which is the song Casta Diva. And you've seen that the airflow are very complex, many things happen there, but there are different situations that you can identify even within the movie. And I'll go back to the movie later, but to identify those different things, you can also measure the respiratory flow rate. So we use a flow meter. Angel is wearing a mask covering both nose and mouth, which is connected to the flow meter, and we measure the flow rate while she is breathing, typically. If someone is breathing, basically at rest, you have something where you have more or less repeatable oscillations, and that you reach a value of flow rate which are above 50 liters per minute, or around 50 liters per minute. Now, if you ask her to speak, the pattern is really different in the sense that the inhalations, the negative value of the flow rate there, are much sharper, but the positive values, the exhalations, are actually less control in a sense. There is no clear oscillation there, and you see only peaks, and those peaks can also reach very high value of flow rate, above 50 liters per minute. So which means that when you speak, you basically might reach larger velocity of the airflow comparatively to breathing at rest, which leads to a larger spatial extent of droplets emitted by a person. And now when we ask her to sing, what we saw was the fact that the inhalation was even sharper and deeper, down to more than 100 liters per minute in negative value. But when she's exhaling, which means when she's singing, actually you see kind of constant value at a very low value of flow rate, around 10 liters per minute, much lower than for breathing and speaking. And the only thing you can notice, which is not exactly constant, is the fact that there is those kind of small oscillation there, which is the use of vibrato technique that opera singers are using. And so now you can try to ask her, or you can detect from the video different, like the spatial extent of the jet you are able to measure with the visualizations, and try to see how it evolved with the different things that we have measured for the flow rate. And you basically see that all trajectories for the air are more or less straight in terms of breathing, speaking. But in terms of singing, you have different kind of patterns. And so the straight trajectories means that in the window we are looking at, we only see inertia of the jet, which means that the velocity is enough to get a straight trajectory over that window. Not the case for breathing, for speaking, but not the case for most of the singing with a wide open mouth, where most of the air is going up very rapidly. And the fact it's going up is just the fact that the air, the CO2 we are visualizing is warm, and so the air exhale is warm and it's go up due to its rise due to buoyancy. However, there is one part of singing when she's closing her mouth for a particular sound, which is the fricative sound F, when she say to fi. And I'll play again the movie. And at the time she say to fi, you will notice that there is a very rapid jet. So the time she's closing her mouth to say the fricative sound F, a very rapid puff of air is coming out, and so if you track that jet, you have once again a very straight trajectory, which means inertia only matter there. But more importantly, if you are comparing the spatial extent, the horizontal spatial extent x as a function of time for all those situations, you see that you have a saturation for the singing in most cases, but for all the consonant sound, you have something which is much faster than even breathing. So that's one of the situations which is more at risk for associated with singing, for rapid and immediate transport of droplets in front of the person. So we did the same thing for a bunch of instruments. And so there is no sound on that video, but if we observe what get out in terms of airflow from the bell of a trombone here, you see that all the CO2, the warm CO2, rise as well at a certain distance. And so you can get the trajectories for different notes, a variety of notes from high to low, but also from piano to fortissimo. And we see that basically the trajectories can be always fitted with a parabolic shape. And why is it parabolic? It's just the fact that you have basically kind of correction here for the origin of the jet. You have here the angle of inclination of the trombone and of the jet then. But you have also a radius of curvature, which is the most important thing. And that radius of curvature leads you to so that radius of curvature here, plotted as a function of the flow rate that you can also measure with the flow meter, tends to be to evolve quadratically with the flow rate. And the reason for that is it's just that you have once again buoyancy versus inertia, and so the very simple scaling you can get is the radius of curvature will be proportional to the square of the flow rate. And you have this kind of new dimension, which is a balance between inertia and buoyancy here. And so by that you can rationalize all the measurements you do with in the real life. I mean, on the real instruments. But once again, all those patterns are pretty small, pretty slow in terms of velocity, which means that the radius of curvature you measure there are much smaller than the one you can get on breathing or that you might expect on breathing. And so that's something you see here as well, in the sense that all the air getting from a trombone for all the notes you can imagine are lower than the breathing pattern you have. So which means that the leading driving force for conveying those droplets will be the breathing pattern from the musicians and not what gets from the bell of the instrument. So that is true for trombone, for many other instruments, trumpets, and others. But I told you that there was 3 instruments identified as risk for the amount of droplet: trombone, trumpet. But there was another one, oboe, which was also identified, and that's not the case there, as I will discuss that. There is also another instrument which is not the case, and it's pretty obvious. It's actually a flutist, because when you play a flute, you inject an air which is tangent to the mouthpiece. And so you see definitely a rapid jet emanating from the person breathing. It's not that great on the screen. But you see it's traveling over the side of the window very fast within less than a second. It's a very rapid jet there. The other exception too that we found was the oboe as well, where when you are playing an oboe, you are actually playing at a very low value of the flow rate when you are playing. Like, you don't need to inject a lot of air. And so an oboe is breathing like a singer, I mean, like everyone else. But when he's playing, you have this weird pattern where the signal that you measure is blue is associated with the music that is playing, or the note that is playing, at a very low value, 2 or 3 liters per minute. It's more or less constant. But he's not able to get out enough air from his lungs before inhaling fresh air. So he needs to basically expel rapidly some air before being able to inhale new and fresh air. And so you see all those peaks in red, positive peaks, which can go up to 100 liters per minute, and very rapid airflow are associated with those peaks. And so if you measure the spatial extent of those jets, basically as a function of time, you basically see the fact that all the knots in blue are much lower than everything associated with breathing or speaking as well. But the red dots here are measurement associated with a rapid, swift exhalation of the oboist between notes. And those ones are even faster than the fastest flow I was able to do on my own, which are blowing in orange there. So it's extremely rapid, and so that's possibly a risk of contamination associated with those flow within an orchestra. And I'll end the presentation by mentioning that, of course, you can reduce the spatial extent of those airflow with a cover on the bell of a trumpet, but also with a mask but still at the end, airflow is going through the mask. The person. And with that, I want just to acknowledge people who make that project possible in the net, and thank you for your attention. I'll be glad to
do you have any questions?
Thank you for really very, very interesting talks on several topics of great interest. On the first topic, the Leidenfrost, I arrived late at the seminar, so I'm really sorry. Maybe you said that before I arrived, but are you aware of some modeling attempts of that, or did you do yourself some modeling?
Yeah. So there was so of course. There was this very simple modeling for the friction, which appears to working remarkably, even despite its simplicity, to be able to predict the thickness on a dynamic way. But for the modeling of the levitation time, typically, we had this kind of dashed line here, which works pretty well with the data, and which works also when we vary the volume of the drop. We are able to capture that kind of effect too. But I think I want to be careful on that kind of model, so I'll tell you what is the model about. But the complexity in that kind of situations in that you have many ingredients for limiting the levitation time. So the first thing you don't know is the amount of CO2 you release at a period of time and how it evolves over time. But there is many things which happen with all the airflow in the sense that the CO2 will escape from the outside of the drop. But now, despite to Leidenfrost, where it's mostly happens on the bottom interface closer to the hot solid, now it will be released from the entire area of the drop. Then you can imagine that the CO2 expelled from the drop or released from the drop will be drained by the airflow due to the vapor flow below, or the gas flow below the drop. But you have also diffusion of that CO2 around the droplets. And most difficult things to model is the fact that you have also natural convection at longer time. In the sense that the CO2 is heavier than the ambient air, and so you might expect the fact that your cloud is not that uniform around the drop. And so what we did on that model was to balance the amount of CO2 you can generate and find the time at which the layer above the saturating layer above the drop will be equivalent to the in terms of Henry's law to the concentration within the drop. And at that time there is no more release of CO2, and so levitation is stopped. And so that's what we did with that model. And for that model, we consider the fact that the limitation there is diffusion of CO2 around the droplets. So we assume a uniform cloud of CO2 around the droplets. And we found that with only an adjusting parameter for the diffusion length of the order of the unity, we found a correct agreement with the data there. However, we were not able to image CO2 at that time, not what I've done on the second part of the talk. But so I cannot say, oh, the cloud is uniform or if natural convection plays a role at that time scale there. So that's still an open question, I would say. I hope it's
okay.
clear
Thank you
enough.
very much. Great answer.
Yeah.
Do you have more questions? So I think it's getting late, so we can stop here anyway. Philippe is here for the whole afternoon, so if you are interested, you can still talk to him this afternoon. And thank you very much for the talk. Thank you.
Thanks.